Good afternoon and welcome to Open Source Software for Mathematics. Our presenter today is Kyle Riley from South Dakota School of Mines and Technology. If you have any questions for our presenter during the session, please feel free to enter those into the chat at the bottom of the Zoom screen and we will address them at the end of the talk. And on that note, I'll hand it over to Kyle.
Well, thank you very much and good afternoon to everybody that's here at the virtual section meeting. I'm glad to have this opportunity to talk to you today about open software for mathematics. This sprung from some work that I've been looking at. I've been very interested in open source materials, which primarily has been book stuff that I've been running through. But then I got turned on to the idea of looking at open source software as well. So this is really just an introduction to kind of help encourage people to think about using open source software. So we'll talk a little bit about commercial stuff that people are probably used to. Then we'll talk about some choices and what's out there for open source software. A few items, I'm not going to get an exhaustive list. There's a lot out there. And then I'm going to do a couple of illustrations, one with WX Maxima and another one that's with Octave. And then we'll wrap things up from there. With that, let's talk a little bit about commercial software that people are probably pretty familiar with. So there's things like college algebra systems, things like Maple, Mathematica, things that do numerical software. MATLAB is something that's required for one of my classes I teach in. There's MathCAD, there's LabVIEW, there's some other things like that. Statistics, there's several different statistics packages. I'm not going to talk much about statistics here, but certainly you've got Minitab, SPSS, and SAS are some options out there for commercial platforms for statistics. There's a lot of good reasons to do commercial software. You have more tech support with commercial software, so you have a place to send students if they have issues. The documentation is usually maintained at a regular rate because they invest in writers and other people to maintain the documentation more. Also, all the infrastructure for distribution and support of maintaining websites, making sure the software works with a variety of platforms. There's more investment in those kinds of things with commercial software, so that's a little bit more robust as well. Development, often these commercial systems, they're trying to outdo each other, and so there's more investment in trying to do new things, new toolboxes, new packages, new other things to incorporate. So that's another advantage they have as well. The drawback is cost. Now for math, the expenses to students is not really as bad for a lot of the math products. Many of the software that's out there that people use in the math community do have a student license that students can get. So cost isn't as big a deal for math software in particular, but students often lack access or they have to pay extra to get the access they need. For example, the MATLAB I use, students can use the campus version, but they have to do it on a campus machine. And if they're not on campus, they have to VPN in order to get to the license manager. And the VPNs often slow things down quite a bit. There's also, with these developments of commercial software, they often align more to industry, which means they might have expectations and needs that don't match what you do in education. Some require expensive graphics cards to work. Others might require expensive support software to work. The licenses can be restrictive in terms of the use. And then the development, if you're trying to create customized tools, the code is often closed source, so you don't get to see it. It's proprietary. And so it's often hard to build customizations that work real well in an embedded sense because you don't know what's necessarily being done on the other end of the development. One of the big reasons that brought me to this journey is I teach with MATLAB, and every day I fire up MATLAB in my class, I get to see the warning message that it's only for classroom, I can't use it anywhere else. And so that kind of prompted me to think and look around to see what else there for other software that one could use. So let's talk about open source software. There's a lot of different things one can get into with open source software. You can, in computer algebra systems, you can look at SageMath. It's a real popular platform right now. We're going to talk about Maxima. Some other ones out there, Math ICS, Magma, or some other ones. There's a lot of computer algebra systems, so that's just a few of them. Same thing on the numerical software side. We're going to talk about Octave, another popular one, Scilab, and then there's the plain programming ones. So the previous talk we had, they went through Python and talked about Python. There's another programming language that's a little bit newer called Julia. It's got a lot of interest as well. On the statistics side, you've got RStudio, RStudio Cloud, are some products on the stats side. Why would you want to go to open source? Well, it's free or it's dirt cheap. Shareware versions are usually pretty cheap to get as well. This makes it easy for students to access both on and off campus. And so that can be really helpful in terms of doing that. Development, you can customize a little bit better because you actually get to see the code. And so that's an actual advantage that you can have in terms of the work that you're doing. Also, there's kind of a strong sense of community with some of these. The SageMath group is a really energetic group. If you see them, their material online, they're quite evangelical about how they talk about their preferred platform. And that's true with some of the other ones as well. And most importantly, from my perspective, is the licenses are not restrictive. So you can use them for different things and you don't have to worry about violating some kind of license, because in many cases, the open source software you can use for a variety of different things, not just the classroom, not just academic research. So that's another nice feature that you have in terms of open source. All right, so the drawbacks, of course, development is the maintenance of the software can be sporadic or it can stop. You're heavily reliant on the kindness of strangers because the people that are maintaining the software are often a group of volunteers. They're not necessarily paid. And so that makes development and maintenance a little bit more sporadic. Incorporation of new innovations often can lag or be lacking in terms of what you're doing. User support, there isn't really a user hotline. There's some community boards and things like that where you can get some help, but it can be a little bit more limiting. Documentation can be limited, or in one of the ones, I often came into the thing that's often old, it's out of date. So you're working on some kind of software, you want to get some help, you look up something and it's a version that's quite a few years back. And so the documentation isn't necessarily kept up to date in terms of how things work. So that's another drawback. So I wanted to talk about Maxima. And so a little bit of history on Maxima. Maxima is a spinoff of Maxima. This actually came out of MIT many, many years ago. So MIT had this computer algebra system they developed from the ground up. They've eventually one of the creators got a permission to try to move this into a commercial outing called Maxima. That did not work out so well. They were able to then roll it over and turn it into an open source project, and that's where Maxima comes from. So Maxima is a product that's been around for a long time. It's one of the older computer algebra systems out there that's been developed as an open source. So it's been around a long time. A lot of people may have used it in different contexts. There's a lot of different versions and flavors. The one I'm going to show you and talk about is WX Maxima. That one's a Windows version, and it is developed with WX widgets. So that's why the WX is in there in terms of the work for that. The setup and structure of it is a lot like Maple and Mathematica, and that's kind of the reason I was attracted to it. I've looked at some of the other ones, and this one really gave a flavor of Maple and Mathematica. And since I'm pretty familiar with Maple and worked a little bit with Mathematica, I found that maybe more familiar to work with and found it easier to kind of navigate. So it was a lot more intuitive for me. You work with worksheets. The worksheets have cells. The cells you can do input, text, or math. The commands are similar to what you might see in Maple or Mathematica, and you have to end them with a semicolon. And to actually run something, you'd have to do Shift Enter to make it work. And so those are some of the things that go with that. Now let's see if I can pull up the Maxima that I have. So I'm going to show you a little bit of Maxima here. So here's the window for Maxima. You can use it like a calculator. And so, you know, just like the previous demonstration, they were talking about calculators. With Python, it does exact arithmetic like Maple or Mathematica would. You can have it do float numerical if you put a decimal. There's actually a float command to basically force it into decimal. So there's a lot of things that are quite familiar. So if if you've worked with Maple or Mathematica, I think you'll find that this is very similar. You can factor, you can simplify, you can do a lot of different things. You can go to the previous command. Some quirky things is the percent sign's got some meaning to Maxima that I haven't completely figured out. For example, if you're wanting to use complex arithmetic, Maxima doesn't really care what I is. It's percent I is the imaginary number. And so that's true for pi as well. Percent pi is what you look for. So the percent sign is something that's used a little bit more in a characteristic for some special functions in Maxima. Low-level things that you're kind of used to, or at least I'm used to, is you can define functions. You can put in variables and do like a functional evaluation. And you can also put in variables and define variables, and then work with those definition of variables. So like, for example, I have this function 32x minus 9c. C is a variable. I can then define c, and then it can use that value later. If I want to remove that value, one thing I liked about this was if you want to delete a value for a variable, you type kill that variable name. So I had defined c. To get rid of the c, I can do kill c, and it'll delete the value for c. I found the use of kill to be a very satisfying endeavor. So, I'm used to MATLAB where it's just clear. Maxima is far more serious about deleting the variables. Expanding, solving roots, all this is very similar to what you might see in Maple and Mathematica, which is one of the reasons I really liked it. The graphing in 2D, just to show you a little bit of that. You can plot, it has all the kinds of features you might be used to in Maple or Mathematica. There's kind of two flavors, well, there's actually a lot of flavors of plotting, but the WX plot forces the plot to be inside the window for Maxima. Now, if you want to actually work with the figure and manipulate it more, you can take the WX off. And then if you run that, it actually goes to GNU plot. Now, I'm not going to do that here because if I bring up a GNU plot, Zoom's not going to capture that. So I won't be able to show you that part. But that's a feature that's nice. So it has the GNU plot features in it, which for those that really like GNU plot, this interfaces with GNU plot, which works really well for that. So you can parameterize plots, you can change the figures, there's all the different things that you can do with plotting. You can take discrete data like I have here and plot that. You can do step functions. You can do all the kinds of things you're kind of used to in terms of plotting in 2D. The same is true for calculus. The limits commands are very simple, similar to what you might see in Maple or Mathematica. Similar kind of syntax. Same is true for derivatives, and you can work with improper integrals and work with things numerically or indefinite integrals. The graphing in 3D is a nice feature, although I prefer going to the GNU plot. So for example, I've got this WX plot 3D for a function in 3D, but I can't manipulate it because in the WX window, it won't let you do that. You have to shove it to the GNU plot for you to be able to rotate or spin the image around. The 3D plotting, I definitely prefer the GNU plot features it does for that. You can do contours. One area that I didn't get to explore as much, I just didn't run into the time that I needed, the differential equation tools. they're a little bit different from what I'm experienced and familiar with on Maple. They do have, you can solve differential equations, you can do directional fields, but the syntax and the setup was a little bit different. So I wasn't able to seamlessly navigate through the differential equations materials they have as much as I could some of the other materials for calculus or some of the other things that I was looking at. So it can solve things through Laplace transforms. It loves working with that. I think it can do all the things that you'd want to do in Maple. It's just the syntax and setup's a little bit different as far as I could tell. All right, so let's see here. Let's go back to my slides. All right, so with WX Maxima, I think if you're wanting to use this thing in pre-calculus, calculus, differential equations, and you're used to something like Maple or Mathematica, I think you'd have an easy time switching over if you needed to or had to go into something like WX Maxima. Sage Math has a lot of materials out there as well, plus a strong user community. And that's true with some of these other software packages as well. But I wanted to show off WX Maxima just to give you a feel for, oh, okay, well, this is kind of like Maple. So I wanted to give you that the familiarity. Another one I wanted to talk about is Octave. Now, I've been using MATLAB a lot in my numerical analysis course. And as I mentioned, the license is quite restrictive. I can use it in my class, and that's pretty much it. That's our site license as a campus doesn't let me use it anywhere else. And so I knew about Octave. I hadn't used it much until recently. GNU Octave was initially created to solve chemical reactor problems. And the Octave name actually is a tribute. One of the creators of Octave wanted to name it in honor of one of his former professors and mentors. So it's actually named in tribute to Octave Levenspiel, which is a chemical engineering professor at Oregon State. So the name is tied to a chemical engineering professor at Oregon State. It's not, there's nothing about music or anything else that's tied to the name. So there's a lot of people that think, oh, Octave's because of music, and it's not. That's not where it comes from. It's tied to the GNU licensing, and so it's often referred to as GNU Octave. And I encourage you to use that search as GNU Octave. If you do a Google search with just Octave, there's a whole bunch of music stuff that comes barreling into your search window as a result. Octave's been around a long time. It has a lot of different operating systems it can support and those kinds of things. And it's almost exactly like MATLAB. It's very similar to MATLAB. And I'll show you a little bit of that as well. So the window, I'll show you the window that I have. It looks very much like MATLAB. You have a command window, your files, your command history. Let me show you a little bit of Octave. All right, so Octave, if you run M files like you do in MATLAB, and so here's an M file that I have. The setup and the working with the M files is almost exactly like MATLAB. And if you have M files from MATLAB, most of them will work in Octave almost seamlessly. I haven't, I have a lot of the lower level stuff I do for my class that I've tested out in Octave. Most of it just runs directly as is. Some do require a little bit of change, but most of the time you can do your M files in MATLAB and still run it in Octave if you're just doing plain MATLAB work. So here's a little simple program I have in Octave. I can go into my command window. This is just a script file. So to run a script file, it's just like in MATLAB. You can plug in the function name. This one's going to do a plot. Hopefully I can capture this with my, let's see, let me see if I can capture the window. So it gives you a plot of a window, and this one's an animated one that shows you basically phase shifting in terms of how it works. The plots, I think, are they're a little bit like GNU plot, so I think it's based in GNU plot in terms of how it works. And you can use it like a calculator, just like you saw with Python. You can, plug in your your values. It'll calculate things out. You can increase what's displayed. You can plot in 3D. You can do all the matricey stuff that MATLAB loves to do. If you love MATLAB, you'll like Octave because Octave is very similar in terms of its setup. Let me go back to the slides here. All right. So also, Octave does have toolboxes, although they call them packages. If you're looking for toolboxes for Octave, the suggestion is make sure you're looking for packages. That's what they like to call them. There's a whole bunch here that I wanted to mention. I highlighted Symbolic because that's probably one that people are going to be interested in, more likely than not. So it does have a Symbolic Toolbox, but it has optimization, fuzzy logic, and a lot of the ones you might be familiar with in MATLAB. You can do numerical work that ties to pre-calculus, calculus, differential equations, and all the other ones here, but this is a numerical machine. So if you want to do things analytically, Octave's not a great bet. It can do it through the Symbolic Toolbox, but it's hard otherwise. To wrap things up here, open source software, it's a nice alternative. It gives you access both on and off. You can customize because the code is open source. There are challenges, distribution, documentation, those might not be as well supported. The development can be sporadic, and reliability can be an issue. There's some quirky things about getting some of the stuff to work that it's not as seamless as it is for a commercial package like Maple or MATLAB or those kinds of things. But it is free, and it's amazing how good this stuff is. That's just free software you can just download and use. And so I wanted to kind of encourage people to think about, oh, well, I want to try Sage Math or something. It's usually a pretty easy thing to go download and try. So I wanted to encourage that. That's all I have for what I wanted to talk about, and I'll take any questions.
All right, well, we didn't have any questions come through in the chat, but few positive comments in there. So thank you very much for your time today, Kyle, and all the valuable information that you shared with us. Our next session is going to begin in about 13 minutes. You can view the chat for session meeting room links or access the conference website for a complete list of sessions and their descriptions. While accessing the conference website, don't forget to swing by the virtual booth to say hello to the Hawks team, view a quick 5-minute demonstration, and be entered to win a $50 Amazon gift card. We'll see you all at your next session.
Thank you.
Thank you, Kyle.